It is my pleasure to invite Dr. Rahul Kashyap from IIT Bombay to
Just a minute, sir.
Yeah.
Shubham, when we start, please stop sharing.
Hello, can you hear me well?
Yes, we can hear you.
Okay, good. I'll share a screen. I'll switch off my video. I'll just.
Sir, we are introducing you. So,
Oh, okay. Sure.
So it's really my pleasure to welcome Dr. Rahul Kashyap from IIT Bombay. He specializes in the study of astrophysical objects using computational and analytical methods. His current focus involves hydrodynamical simulations of binary white dwarfs and binary neutron stars mergers and the resulting transients. He's also interested in combining insights from gravitational wave data analysis with other physical constants, and he's active member of LIGO Virgo collaboration and the Cosmic Explorer design and the studies team, where he contributes through hydrodynamical simulations and gravitational wave data analysis. And specifically, he's working on hydrodynamical modeling of kilonova ejecta and exploring astrophysical implications using parametric Bayesian interferences from individual gravitational wave sources. Today, he's going to explore two key areas of astrophysics where computational methods have driven significant discoveries: the structure and evolution of stars and stellar clusters. So he'll go into the analytic formulation of numerical implementation of equations governing these systems and discuss specific solutions using both analytical and numerical techniques. And then, of course, he'll give some guidance for future study. Yes, thank you. Please.
So you are on mute, sir.
Thank you very much for your kind introduction. I'll just quickly go to the. So I hope you can see my screen. Okay. I can see a test on Zoom. But I hope you can also see. I'll switch off the video for future things. So for thank you for coming up to all the students, and today basically I'm going to talk about some general framework of computational astrophysics, which comes.
Can I interrupt a bit? Would you be taking
Sure.
questions during the lecture, or you will prefer them at the end?
I'll prefer if the students can write the question in the chat,
yes.
And if like if you can just like every like some time like 10 minutes or something,
Okay.
I'll stop and see questions on.
Okay, so you'll see it yourself. Okay, fine.
Yeah, and you can also maybe someone can monitor who, like, if there are some like what kind of questions are there. Like I'll also look at it, but
yeah. If there is something which is crucial for further understanding, then we'll interrupt and ask.
Yes.
Otherwise,
Sure. Okay. Yes. Okay. Yeah, so yes, please don't hesitate to ask questions in between, because some broad understanding is important, and some steps are very crucial for future steps. So as I was saying that I'm going to talk about in general astrophysics, the computational methods in astrophysics as it is applied to understand uh, objects that we observe, and which comes largely under theoretical astrophysics. So we should not see computational as a separate part of astrophysics, but it's a separate skill set which is required to solve the same problem that astrophysicists have been solving using analytical methods. So broadly, here, as you can see on the screen, I've divided some major chunks of major sections of the astrophysical research, where what we do, the broad idea in astrophysics is that we apply the physical laws that is found on Earth to the astrophysical systems. I'll zoom in a little bit more. And when we apply these physical laws, our purpose is to understand the conditions or properties of the systems which produce such an outcome. For example, we see stars, galaxies, clusters of stars, and we see them only using light. Now there are other kinds of signals that comes from them. So mainly electromagnetic waves, that is light in all different wavelengths, but also high energy particles like neutrinos, electrons, protons. Uh, so these so we want to understand that using only these observations, that what are the properties or conditions of the systems. Uh, and But astrophysics differs from other applied physics in the sense that we can also test whether our the understanding of the physical laws that we found on Earth is true or not. And that makes it very unique because astrophysics has given us reasons to believe that many things that we understand about particle physics is not correct. So, for example, uh, I so in when we applied our understanding of energy generation to sun, we found that that the neutrinos produced from the sun that was observed on the detectors on Earth was not as predicted from the theory, and that led to ultimate understanding that neutrinos change their flavors. They come in different flavors, where flavor is a quantum mechanical property, and they oscillate between them. And once we account for that, then we can explain. So similarly, we found by study of type 1a supernovae that our universe is expanding at an acceleration with at an accelerating rate, and the and that led to infer that there is an extra component of energy in the universe, and we call it dark energy. So we also test systems. So now if you want to test, or even if you want to just apply, so in both of these things, we want to first model the system, model any astrophysical system that we are observing as best as we can, applying the physical laws from the first principle. But there are always some limitations, so then we go to approximations. And this is a very important point because uh, sometimes we think that in fundamental physics, we are if you make so much approximations, then we are those are not actual research because you are applying fundamental physics laws, and there is nothing new that is being done here. But to infer the properties, from the observations, you need to solve the equations, basic equations for that system, and sometimes it is not possible because equation is too complex to solve, and sometimes decades or centuries are like pass by before we get to any solution. So approximations are very crucial discoveries that is made by mathematicians and also physicists, astrophysicists who work in this. Uh, Other thing, after modeling the system, we find observable. So modeling the system means like how do we describe it? For example, we describe it as a fluid, or we describe it as a collection of photons or a collection of small particles. How do we describe, and then what are the observables? So not all properties of astrophysics system that we are using to model can be observable, because if you look at the sun, the temperature at the center of the sun will be very high, but we look at only temperature at the surface. Density and all other properties that exist inside the sun in the interior are not observable to us. What we see is only outside temperature and luminosity, and then also we can measure the mass of the sun by observing the motion of planets. But other things, internal things, are not observable. But that doesn't mean that we cannot infer these properties that is inside the sun. And that is where the modeling comes. So we can model that how temperature and density varies from center to surface. And by matching with the data with the surface properties with observation, we can say with very high confidence that internal structure of sun is so and so. Okay. And when we go to this part, then we have to come to computational modeling, because the approximation that is used in computational modeling is supposed to be a smallest approximation, because if we are doing analytical calculation, then approximations very large and sometimes unphysical approximations are assumed, because we cannot solve the equations by hand. But if you can use computer, then you can go to much more general situations and solve systems. But here also there has to be some sense of limitations, that you cannot just solve motion of every atom and electron in a star and find out its luminosity. So we again go to some approximations in when we do computational modeling, and then but that leads to some errors in modeling, and also uh, we have some errors in observations. So then comparison between observations and modeling become a bit complex, and the current best framework to compare to any modeling, in physics and observations are comes under this Bayesian inference framework. So you have to have a description of a model, and compare it, and then we obtain that the parameter of the model, that is described, uh, that is compared with given an observation that is inferred, and that comes under this Bayesian inference pipeline, in which instead of having a value, we get a probability distribution of those parameters. Okay, so this was very broad outline. So I will quickly now delve into. So just to remind me, we have 1.5 hours for one lecture, and then another 1.5 hour for with some gap. Is it?
Yes,
Or one?
that is right. Yes.
Okay, great, thanks. Okay. So now we'll come to observations. So as I described earlier, I'll just briefly describe what are the main observations. I think you guys already know this. I was following the assignments and other chats on the Google Classroom. So you are familiar that we observe a universe mainly through electromagnetic observations, through radio uh, and optical, X-ray, gamma ray, and other in between uh, uh, electromagnetic waves. And but in addition to that, we also have high energy particles like neutrinos and all. And very recently, we have also observed gravitational waves that is directly coming from the binary stars, because these are the specific conditions which are required to produce very strong gravitational waves, and that we have observed. So, so the new avenues that have opened in astrophysical research is to combine the information that was coming from electromagnetic with gravitational waves, and as well as high energy particles. So uh, there was already a synergy between these two, high energy and electromagnetic observations for example, our sun and supernovae. And we learned a lot about using these two synergies. But the gravitational waves that has has become a new member of this, what we call multi-messenger astronomy. And this is something also is very important frontier in astrophysics. But today I will just touch upon this, that how it connects to our astrophysics, traditional astrophysics research, and uh, how it is going to impact some of these fields. I will not discuss the full thing, but just touch upon it. Okay. Sorry. Okay. So now we can go to actually some broad properties of astrophysical systems, and that starts from virial theorem. So what is virial theorem? Virial theorem actually connects two different properties of the same system. And the idea is that by observing one, we should be able to guess or find out the other property. So first, just some proof. So here, as you can see that first, there is a quantity that is constructed out of momentum and the position of n particles. So here there are n particles distributed in the field, and each one has position ri. This is position vector, and I constructed a quantity which is sum over momentum dot r, momentum dot product with vector, the position vector, and then we want to calculate the time derivative of this quantity. So if you do that, then first, as you can see that first the d by dt will go to r. So from this, this will become r dot, so that goes here, and then you have p here, and the next thing will be you'll get d by dt here, so that goes p dot and then r, and then if you do this integration over some time interval tau for some time, and you take the average of it. Okay, so it will be clear like why are we doing all this, but this can be called as kind of an averaged quantity, time averaged time derivative of g, and that on the other side, if you do, then you can see that this becomes essentially v dot multiplied, so this comes kinetic energy, 2 times kinetic energy average, and then this quantity here can be written as p dot, can be written as f, and then dot r. So that gives you f dot r is the work done on ith particle, and if you sum over all, then you get the potential energy, total potential energy of the system. Sorry, just a minute. I'm sorry about the disturbance. Okay, so in the end, basically, if G is periodic or tau tends to infinity, so if G is periodic, then this integral will this will repeat itself, and tau will remain same. So this becomes 0, or if tau becomes infinity, then this denominator will become very large, and this will become 0. So in other case, the total 2 times kinetic energy plus potential energy, that becomes 0. And that leads us to the result that potential energy is 2 times kinetic energy, barred from the sign. There's also a sign here. So this type of thing can be used for any collection of particles. Actually, this has been first time used in the context of gas in a box, and these identities have been derived. But this can also be applied for mutually interacting particle, where the mutual interaction could be gravitational or something else, some other kind of potential. So let's apply this. So I'll just check some questions. Okay, so there was a question: what is flavor of neutrinos? Okay, so I think this is already answered. Oh, tau. Tau you mean in the integral, right? Yeah. So tau is just a time. It's you can just write it t, or no, tau is a time over which we are doing this integral of g dot d by dg by dt. Okay, so this was something. What is pi? Pi, where is pi? There's no pi here. So then this next question is, what is the exact significance of this virial theorem? Exactly. So that's where I'm coming to. So why do we do this? This theorem is very powerful because it doesn't talk about what are the mutual interaction. So how they are interacting, and so this relation is 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 always valid even if there is, you don't know, mutual interaction. If there is some we have some ignorance about that, even then this relation will be valid, and this allows us to probe a lot of different kinds of systems. Okay, so how do we use it? So let's use it for different type of context. So for example, one very simple thing that we can derive for a single star is this relation, that the kinetic energy of all the particles in the star will be this capital N. This is all the particles, number of particles or gas atoms in a star, and then this 3/2 kT will be the total energy per particle. So this is the total kinetic energy of the particles, and then this can be equated to potential energy of the star. So being please bear in the mind that this factor 2 is not that important. If you will do this calculation, suppose numerically or more carefully, and this tau is not going to infinity or some smaller values and things like that, then this factor will change depending upon context. And also, if you have other kinds of forces that can go there, then or other variables, then the terms that comes here are there are more type of terms that comes. So, but in the end, the main point remains, which is that the global properties of the system can have some relation between each other, even though individual particles have many different variations among them. So, for example, for a single star, if you just equate these two, even with factor, you get the simple relation that T goes as m over r. So what this means is that if you fix the mass of the star and somehow it is compressing, so for example here there is a compression going on, then in that case, as the radius will go down, it will become smaller, the temperature will go up. And this is a very general result that happens because, and as you know, this has to be true because when you compress a gas, it becomes heated, and then its temperature will increase, then the pressure will increase, and then again it will resist that compression. So now if you apply this relation to a globular cluster, then you can imagine that the total so by the way, the global cluster is a collection of stars that is mutually bound to each other with mutual gravitational force, and they evolve uh, according to Newtonian gravitation or Einsteinian gravitation if there are black holes and close encounters. Okay, so there is one question that the system has to be bound for applying the virial theorem. Yes, that is true because as you can see that we are doing a finite sum here. So if the system is unbounded, then this thing will diverge. Even this thing can diverge. So we always have to assume some subsystem of a big system if we're looking at or a closed system, so that this thing doesn't diverge. Okay, so for a cluster system, what we can for a cluster of particles or under mutual gravitation, this we can also write this as total kinetic energy, where each mass and velocities are known for a particle, and the potential energy again can be written as the total mass of the globular cluster divided by r, where r is the size of the globular cluster. So now you can see that where this could be useful. So for example, suppose there are mainly similar types of masses in a cluster, just mass m, and the total number is n. Then so for example, okay, so let's actually forget about this one. I should not say this. So yeah, forget about this part. Just focus on this thing that, so if we have kinetic energy of all the stars that is summed over here on the left hand side, and on the right hand side we have total mass of the globular cluster along with its size. So now this we can see from Earth. For example, we see a globular cluster, we see that their sizes are something like this. So it will have some angular distance, and then if you know the distance to the stars, then we can calculate what is the size of it. So that goes in the denominator. The velocities we can measure by Doppler shift. So some stars will be going away from us, some stars might be coming towards us. And by measuring these Doppler shifts, we can measure their velocities. So now using this relation not used in this form, by the way, it's a bit, it becomes a bit more complicated. But using this relation, we can find the mass of the globular cluster. So what this tells us is that the way velocities are distributed of stars in a globular cluster is connected with the total mass. And this relation has been used for lots of different types of uh, objects, not only globular cluster, but also galaxies and also clusters of galaxies. And that helps us disentangle the redshift that is observed from these galaxies, and also helps us uh, in estimating cosmology, or cosmological parameters. Okay, so these things I will leave now. Okay, so now I'll come to just describing very broadly some the physical concepts that will be used here, and I want to point out that I'm going to use this T. Padmanabhan's book, Tanu Padmanabhan's book, Volume 1, whose name is Astrophysics. I think astrophysics of stars, or theoretical astrophysics. Yes, it's called theoretical astrophysics. So there are 3 volumes, and these reference that I'm giving here of the sections are from volume 1. So I'll come to very briefly that what are the main components. So for example, when we want to model a star, we know that it looks more like gas. It is just fluffy gas, uh, but less like a solid object. Okay, and this
Just a request, sir.
sorry.
Just a request. If you can close the bookmark, probably better zoom
Oh,
view.
okay.
Thank you.
Okay, great. Thank you. Okay, so first, to model a star, we know that they are collection of that it's a ball of gas, so it has to be modeled like a fluid. The fluid differs from other objects, for example, solid, that it cannot withstand a shear stress inside object. So, for example, if you have a some fluid body, and then there is the fluid is filled inside, and then if you apply some force to it on some internal object, some internal element of the fluid, it will just move. It will not resist it will not give you any stress. But during movement, you will get a force that will be proportional to the rate of movement, or rate of motion of this fluid element, but it will move. It will not go back to its position. That happens in the fluid, in the solid. Sorry. And that is the property of the gas that we see, and that's why we model the stars as a fluid. And that turned out to be, but how do we know precisely, right, that this modeling that we are doing as a fluid is correct or not? And that actually comes from the our exact comparison of this model's outcome observables to the observations for stars that we have seen. So I'll touch upon that also. Okay, so there is some question there. What is L in global cluster? Was it discussing L? Was there L somewhere? There's no L here. Oh, okay. Then there is a question: if radius increases, never decreases, then our arsenal is increasing towards radiant, then its temperature decreasing. Yeah, so that's a good question. Yes. What? But it happens if you look at the causal relationship, then you'll find that actually what happens is first the fuel runs out. So, for example, our sun will use all the hydrogen slowly, and then the generation of energy or photons at the center will stop, and that causes gravity to be to pull. So I'll come to that part. So in terms of physics, what you require is basic equations of fluid dynamics, thermodynamics, and radiation. These are the three things that is important for to model star. But the energy generation that happens in star is nuclear reaction. Is through nuclear reaction, so that also becomes very important. That is different from the fluid that we see on the Earth. And then there are some other crucial things. So I'll come to all those things when I'll discuss the model. And then I'm not sure how much time I'll get to the n-body system, but essentially, if you have lots of particles or stars or galaxies, each of them could be anything in your model, and they are attracting each other, each of them. And then this force between any two I and j particle can be written like this, G over R square. And then if these particles are not individual particles but as continuous system of gas, then here the potential, this can be solved as using by solving the Poisson equation. One crucial thing is that when we model these particles as using Newtonian gravitation, we are ignoring the or we are assuming that systems are not relativistic. That means the velocities will not be very high. All of these individual stars are not compact objects, and they are close encounters, which in which relativity or general relativity becomes important. Those are not happening. So in other words, this using Newtonian gravitation to model stars is valid for example, globular cluster, outer region of globular cluster, and between main and attraction between or modeling of a collection of main sequence stars, not, for example, a collection of black holes and neutron stars, then this theorem will fail. So we are not doing that, and there are a lot of approximations, and this is a kind of frontier in the field to model a collection of compact objects using general relativity theory, and there is still some research is going on. Now, in terms of math, what you need to know here is the system of ODEs that, any system, for example, here you have three variables whose dy dt is written on the left-hand side is equal to some matrix where these matrix elements depend on these variables and again multiply to some x vector. So if you know how to solve this type of system of equations, then you are good to go to solve these n-body systems, these ones. And if you know how to solve this partial differential equation, for example, if I give you this potential phi, if this is your equation and you have to find the potential phi, then we first find a function g, which is a solution of this equation. So if you apply the same grad square to g, you'll get delta function. If you find such a function, then what will be the solution of phi? Anybody want to guess? So, are people aware of this? Or okay, so so the question is that I'll repeat the question. Question is that if we want to solve this equation, okay, so this we have to solve. I'll just write it. So we have to solve this equation, and we have already found a function g such that this is true. Okay. Yes, Green's theorem, that is true. So Green's theorem, how is Green's theorem used here? What we do, we say that if there is such a function which when grad s bar applied to it becomes delta function, then the phi becomes this. Okay, can you see? So this solution actually becomes this. So this essentially tells you that this given distribution of the function, it is very easy to solve. This is because this depends only on this operator, right? Because no matter which function you have here, you just have to put it here because this g will remain the same. But it turns out that g depends on boundary conditions, by the way. So, but this is the most general theory, analytical theory, which is also helps a lot in the numerical computation. And finally, if you get the time, we will see that how for n body systems, we can just loop over all the first mass and then loop over all the second mass and then calculate acceleration. And then we can numerically evolve each of the particles. So I'll come to that briefly. Okay, so when we apply the physical physics, okay. Okay, so there are some questions about PN corrections and all. I will not be discussing that. Otherwise, there will not be any time for anything else. And so I'll just say one thing that PN corrections comes from solving directly Einstein's equation and then going to the limit where velocities become small and so on. So, okay. So when we first applied the physical laws to stars, there were a lot of confusion. So for example, people wanted to understand that how how are stars powered, like where the energy is coming from, and so to understand that there were a lot of hypotheses. For example, one hypothesis was that the gas is contracting at a rate, and because of contraction, the energy is produced, and that energy is what comes out of the sun and reaches us. Now, so if you want to calculate that rate, then you'll find that the rate has to be something connected to this, that this dq dt has to be related to this p dv dt, and p dv dt is connected to this r square r dot. And so that means this r dot, if you know the energy which we observe from the sun, which is the L dot, luminosity, then using this, we can figure out that how quickly the radius will shrink of the sun, or how quickly even the energy will run out. So for example, we can also say that if the total energy that is being converted into heat is coming from the gravitational contraction, then if this is the total gravitational potential energy of a star, then and this is the luminosity of the sun, then this is the total time over which this will exist. So this is order of magnitude calculation that is done in astrophysics all the time. And then it turns out that this is very small time. So if you do the calculation, you'll find that this turns out to be like 10 million years or so. So this is very small time because we have seen artifacts just on Earth much older than this. So that means sun cannot be younger than this or around this age. But it turns out there is also one very smaller time scale. So I'll come to that later. Then the other energy source that was actually opened up by research work of Hans Bethe in 1920s and 30s, who pointed out that stars are powered by nuclear reactions, and he actually did full calculation of hydrogen to helium using the nuclear theory that was understood at that time. And then he came up to this model of our star, of our sun, where this turned out to be very accurate. So to understand this on the order of magnitude, what we understand is that, so for example, if you multiply if two deuterium goes fuses and then forms a helium, then there is a mass defect. The mass of the 2 deuterium will be slightly larger than the mass of the helium, and that uh, defect in the mass becomes energy according to the Einstein's formula. And the part of the mass that becomes energy is generally called efficiency of nuclear reactions. So how much of the mass is becoming energy? So that is a quantity that is defined here as epsilon. And this epsilon turns out to be something on the order of 10 to the minus 3, 0.007 or 10 to the minus 2. So now if you multiply that, suppose total sun's mass converts to energy, so that will be m naught c square. But only part of it actually becomes energy, other will remain as sun's mass, and that is the epsilon factor. So now if you divide that by luminosity of the sun, then that turns out to be 10 by 11 years. And that is the correct ballpark of that could be true at that time. People understood that yes, this could be true, but actual age of the sun takes a little bit more to understand, and that will come to in a bit later. So and then there is another time scale when the star, any star is shining. For example, for our sun, when it's shining, the light is doing some lot of random interactions with the gas, and then it takes about tens of thousands of years to reach the surface, and then directly it reaches to us in 8 minutes. So here, outside it spends 8 minutes, inside it spends about 5,000 years. So when this is happening, you can always say that why doesn't sun ever contracts? And then basically at that point, we have to understand that if sun contracts, then uh, how the physical processes inside the sun stops it from contraction, right? How does it holds or knows about the contraction of the sun, and at what time scale this can happen? So since we are doing order of magnitude, we are not interested in exactly solving full equations. So let's just assume some extreme case. So there's a question: is that a mass defect? Yeah, so that is called mass defect because early times when people doing nuclear reaction, they found that the mass is a bit less than, but that was becoming energy. So yeah, so okay, so in the order of magnitude calculation here, so let's assume that there is some particle at the surface of the sun or any star, and it's freely falling towards center. So its acceleration would be this one, gm over r square, and we'll write its time derivative as d2 r over dt square. So we'll just say that that this this will dimensionally will become r over t square. This t is the time over which it will fall through radius of the star, and this side will be gm over r square. So from this, when we'll calculate this time scale, this is also called free fall time scale or dynamical time scale, then it will turn out to be very small. Okay. So what does this signify? This signifies that when if a particle or a layer of a star falls or contracts, then in 1600 seconds, this effect or perturbation of pressure will propagate to the center of the sun, and then it will come back, and then it will react, and then the pressure difference due to this compression will again come back and balance the star. So this constant contraction and expansion is happening, is going on continuously in the life of star, and that happens over this short time scale. So one small exercise you can do is you can try to convert this time scale uh, to some non-dimensional or some scaling with respect to the sun's mass and radius, and you can find out what are the exponents and the factors here. Okay. So now we'll discuss self-gravitational system, but before that, we have to understand that how fluid systems are analyzed. Okay. So very brief description of the fluid. So for example, here we are looking at uh, uh, a, a box, so for example, a pipe where fluid is flowing, and we take a small element of the fluid and we want to look at what is going on inside it. So if you look at the very small section, then you'll find that these are fluid is made up of atoms and not atoms, actually molecules and so on. But if you look at the small element of the sun, then you'll see atoms, electrons, uh, and free protons, because that's just hydrogen atom stripped of electrons. You will also see some other type of particles like neutrinos and all. But we are not looking in a very small volume, so such a small volume that in this box you see a handful of particles. We are looking at a small volume which is so large that the number of particles here is of the order of Avogadro number or larger. So in that case, what will happen is that we can define at every point a continuous variable, which we call mass density. So to be more precise, if you make so again, if you take the small box and if you sum over all masses of all particles and divide by the volume of this small volume, then we will see that this will be the density, right? Total mass divided by volume. But if the box is very small, then this will be the numerator, the total mass will fluctuate a lot. It will just go some random. But if if a box is very large, then it will become a constant value with very small fluctuation, and that's when we say that we can define a continuous variable which we call density, and similarly velocities and temperature and everything for these differential volumes. So and that is the starting point of defining a system as continuous system, where all the properties of the systems are varying continuously, and we can model it as fluid. Okay, so I'll just stop here for a few minutes and then take some questions. Okay. So can you please repeat which part? So that I shouldn't technically for the fusion of the it takes much energy than is found in some still wise fusion cycle sustained. Okay. So the actual reactions, nuclear reactions theory says that two deuterium or hydrogen uh, or any, or as a matter of fact, any two nuclei, for them to have to come close together, they have to first overcome their repulsive force because both are positively charged. So they have to like overcome this repulsive force, and that can happen only at very high energies. And but if they are at very high energies, then they can just go past each other. So there has to be a very delicate uh, energies at which they can do a fusion and then produce energy. So this and in addition to that, sometimes these reactions are not possible if there are not other elements possible present. So that was what was found in the work of Hans Bethe. He found that just having deuterium is not enough. You have to have also some nitrogen in the material, which acts as a catalyst, and that leads to other pathways of making helium from hydrogen. So that leads to CNO cycle and all. So okay. Okay, so I think okay, so some quick recap. Okay, free fall part. Okay, yeah. So I can do that. Go there. Okay, I think it is here. Yes. Yeah. So I think some this we will see this effect once again. But essentially the point is here is that if what is the smallest time scale over which any process can happen in a star, and that is what we call the free fall time scale. Like, you assume that there is no other force but only gravity. Okay, and this kind of situation also occur in the situation where you have core collapse, supernovae, or things like that. What happens in this case is that the whole the envelope. Okay, so let me just draw this. My battery is running out. So suppose you have a star like this, and this blue star. Then what happens is suddenly all the shell starts contracting because there is no force that it can sustain, and then all of this suddenly becomes a very small object. So this is about, let's say, this so this will be like a core of a star, so it will be something like 10,000 kilometer, or like 6,000 or 5,000 kilometer, and this will suddenly become about 10 kilometer. So it will become 100 times small, but same mass. All of the mass will just get converted to a very small blob. So everything on top of it. So if this is the core of the star, then all. Okay, so actually I to first make the core of the star. So let's say this is the core of the star, which is contracting, and this size is about, let's say, 5,000 kilometer. So this thing becomes a small star, and on the top envelope, which was there, is still there. Okay, and now it will start falling. Okay, so now you can see that there is very little mass left in the envelope, and all the core has collapsed to form neutron star in this case, or it could be even black hole. So what will happen to this? This will, at what time scale they will fall? So this is the time scale of free fall. Okay? So this is the direct physical interpretation uh, of the time scale, uh, and this becomes important in the case of core collapse supernova, for example. But this also gives us the idea that if a star does perturbation, some small fluid moves from one place to another, then this sends a pressure wave which will travel at the maximum speed which corresponds to this time scale. This is the fastest. Nothing can travel faster than this as a hydrodynamical system over the whole star. Of course, light is traveling between the molecules at the speed of light, but uh, that uh, uh, doesn't mean that the whole star will, photon will travel through whole star at the speed of light. Okay, so quick recap is asked. Actually, I didn't do, from the physics point of view, the important thing that I discussed is virial theorem. And then after that, I discussed some mathematical methods that is used here. And
Sir,
now,
there was somebody who had asked about, can you give a significance of virial theorem? So maybe in the recap it can be done.
Okay, I had discussed that actually. So and significance of virial theorem actually just goes into, for example, these two applications, and the most important application that is used is in the case of globular cluster or galaxy clusters, where by measuring the velocities of the individual galaxies or individual stars, we can find out the mass of the star. Okay, so this is how this is the one of the most important aspect of our application of virial theorem. So just to give one flavor, but I'm not going to discuss that yet. But so suppose if you have also magnetized plasma, then virial theorem involves also an integral of magnetic field over the volume. So that means it can also tell you about magnetic field if you are interested in that quantity, and if you can measure other quantities. So for example, here virial theorem connects velocities, that's where there's represents kinetic energy, and then potential energy that is reflected through mass, but also magnetic field will come if a system is magnetized. So that means that suppose if you know these two, then you can find out the magnetic field as well. And if it is important or not, it can be, it could be the case that magnetic field is not important. In that case, only you have these two. So, but this is, if you are interested, you can read the works of Chandrasekhar, and there are other resources on the virial theorem that you can refer. Okay. So there is a question on mechanism for nuclear reactions. So that I'm afraid I won't be able to discuss. So maybe some other time. Okay. So let's go to fluid approximations. And so essentially what we say in the fluid is that if there is a large fluid system, like for example, a pipe where you have fluid and then there is a variation of density, some wave is going on, and here density is higher, here it is lower. So this variation of density at which this density variation happens is basically this quantity d rho over dx, and on top, if we divide the density and a typical density value with this variation, then we get the length scale over which density is varying in the system. Okay, so let's recap this part. So first we say that a star is a ball of gas, for example here, and it can be described as a fluid. And every point, what does it mean by to be described by fluid is that we can describe uh, a star as a 3D field of basic variables, which could be density and velocity and temperature, like to the very minimum, but there could be other quantities as well. But every quantity that we define is continuously differentiable. So we can write its derivative. That is the main point that you should keep in mind. And once you can write derivative, that means you can write its derivative with respect to time. You can also write derivative with respect to space. And these are the basically differential equation or equation of motion of any system, right? So if you know the density if you know such relation, that equation, that how density varies with respect to time, that means given a density at initial time equal to 0, you can find the density at next time, right? Similarly for velocity, suppose you have an equation for dv dt. So if you are given an initial condition, then you can always find the next the velocities of all the gas elements at the next time step. And similarly, you can just keep on hopping. So I'll come to the numerical part, but so let's just say, how do we actually derive such equation? And I believe that derivation is very important if you want to get the grasp of like applications of fluid dynamics, especially in astrophysics, because that's where some of the limits are reached of fluid mechanics. So whatever I said, the assumptions that we are using describing it as a continuous variable, those things might break. So if you know the derivation, then you know where it is breaking, and then you can go to some other system to describe. Okay, so what do? We say that let's assume this small box. So you remember this small box which existed, for example, here. So you have a water from a pipe that is coming from the pipe and falling on the floor or whatever. Then you will imagine a small volume of this water at this point, and then we apply Newton's law to it. Okay. So before Newton's law, first we apply just mass conservation. We say that what is the total mass inside this box? Total mass will be basically this quantity, right? Rho times delta x, delta y, delta z, right? I should just write this down. So density times volume, that's the total mass. But how does this mass changes? This mass will change only if some fluid leaves the system from its surfaces, right? It cannot just disappear and come some other place, right? It has to go through the surface. And this is the consequence of local conservation laws, that we want to make sure that not only the total energy or momentum or mass is conserved of a fluid system, but also it is conserved locally. Locally means that uh, the to change the mass or any such conserved quantity in a small volume like this differential volume, it has to go through the surface. So how much energy or mass will go? So rho times u times delta y delta z. If you're taking this surface, then in delta t time, it will travel how much? The velocity at this point is time delta t, right? So now it will form a cuboid of volume what? So rho times u, and this volume will be u delta t times delta y delta z, right? So this will become delta v, volume of this small slab that is traveled by the fluid in delta t time, and rho is the density. So density times volume, this is the total mass that actually left this box through this phase, right? Phase 1. And that is what is written here. This is rho u at x plus delta x. And then similarly on the other side of the phase here, that will be written rho u x minus delta x. And then we just subtract. We say that this came in, this is leaving. So the positive x is defined in this way. So this is leaving, so this will be negative because it is we are writing del m del t, so this is a negative, and then this will be plus because the mass is going in. And if you do that, then you will find out that for the x part, you will reach to this part. That the del rho second thing we'll do is the Taylor expansion. So it is defined at the center. The rho is defined at the center, and then we do Taylor expansion at this point. And then this gives us del rho ux over del x and multiplied by this volume. And we did this for x. Similar thing you can do for y and z, and you'll get similar quantities. And this is the famous divergence that you have seen. If you take these three together, they go and become divergence of rho u. Now at this point we say that m is rho times delta x. Now for this to be true, so we just say that take this on the other side. Now we have multiplication of two quantities equal to 0. Now for this to be true, delta v is arbitrary, so we can make it whatever we want and at any point we want. So this will be positive, sometime large value, sometimes smaller number, but still this is 0. That means this has to be 0. And this is what gives us the continuity equation. Okay. So this is our first conservation equation. What did we conserve here? We conserved mass. This is conservation of mass. Now similarly, we will do again conservation of momentum. Okay, so this I had sent some abstract. So this is from one such book. This is an engineering book. Like being physics student, you should not feel that engineering books are not good, especially if you want to understand some topics very well, then they might give you more physical understanding. So there is a question called where is the delta V coming from? This delta V is same as this delta x, delta y, delta z. Okay. So okay. So you should look at some engineering books, and this particular thing is taken from Fox and McDonald. But any book will work where you can see explicitly all the derivation of the terms. For example, for the momentum equation, what we do, we will again apply the Newton's law. So like I will just write down here. Probably this in this context it will be better. So suppose your momentum will be how much? So you have rho, that is the density, and then rho times delta V, that will be the mass, and times U, right? This is the momentum. And now we want to say that this, how does the momentum changes? Momentum changes according to forces, right? Rate of change of momentum is just forces. Now, what are the forces? The forces are acting first, just like mechanics. When you take the box and then you say what are the forces that is being applied. So there could be a string that is being pulled. There could be a gravitational force. There could be a pressure force on the surface. So all of these things are decoded into one quantity that is known as this stress tensor. Okay. So these things could be a little bit unsettling, but if you just give it a time, it will become very comfortable. So a stress tensor is what? A stress tensor encodes all the forces that is acting on the surface. So for example, if you take this surface, if you say that the net force that is acting on this surface is this way. So I'll just actually make a new. So suppose this is the face. This is an arbitrary surface, and then net force that is acting on it is in this direction, F. But this force on this face can be decomposed into many different components. So for example, one along the surface, along one direction, there's another direction, and then one perpendicular direction, right? So three components you can make of this force, and these three components are then again called these three different components of the stress tensor for x direction. Okay, so this is only for uh, this face, because the surface normal is also another quantity here. So we say that what are the forces that is being applied here. So we say that there is a tau axis that is applied perpendicular to it, and then there will be a shear force that is acting on the y direction, and there will be a one acting on the z direction. So there will be three force or what we call the stress tensor that is applied on this face, and similarly there will be one for the y direction. So if you know this quantity at this point, then you can calculate at the two different points in x direction using Taylor series, and similarly you can calculate the in the y direction using Taylor series, and similarly in the z direction. So this quantity, this tensor, encodes all the forces that is acting there. Okay, so okay, no question. Okay, so now these forces, how are they applied? So as you can see here, like this is just one example. So what is done here is that the sigma x, which is the one component or normal component of the stress tensor, is just multiplied with the dy dz. So here dy dz is again this part. So this is the total area times stress. This quantity gives you the force. Okay, so this is how it is defined. And similarly, you then apply to this face as well using the Taylor series that is done here. So to plus dx by 2 and then minus dx by 2. And not only that, we also apply the shear stress. So force that is acting parallel to the surface. And those are also Taylor expanded, although in different directions in y and z. And then the total force in x direction that is acting on this block is this. So three components of the stress and three derivatives. And along with that, there is also a gravity force that is acting on the whole fluid body, and that will just be rho g. So that will come here. This is force per unit mass. So now if you combine both of them together, then you get these set of equations. Okay. So this looks very complicated, but if you just condense it, you can see that this part of the equation can be written as rho and then del u del t, this part, and then you can write it as u dot grad and then u. Because it is x, y, z, 3 directions, and so this can be written like this. And the other side can be written as rho and g vector. And just a minute, let's move this here. And the next part can be written as del. So here they're differentiating with sigma and tau, but I'll just use one, tau ij divided by del xj. So to make it consistent, I will just write the notation like this: ui, ui, gi, and here. So xj, this will be summed over that. So this is sum over j. So like this, we can write. Now at this point, I will refrain from going into the full theory of this equation. I'll just assume that the shear stress is 0. So this is in contradiction to what I said earlier. I said that fluid is something that applies gives some force if you push a fluid element, and that is viscosity. But what we are assuming here is that there is no viscosity, and that is true for okay. So there is some question. Okay, yeah. So I'll go a bit slow. So any question you can ask. Okay, I'll actually go. So here, this will become again very simple. This is just what we'll do. We'll say that only the diagonal component of the stress tensor will survive. So we'll say that only this, and this term will survive. These are all zeros. Okay, we're just saying that this, meaning that there is no viscosity. So all these are all becomes 0. And then here at this part, we are left with only pressure. Sigma x is minus p according to our construction. So then this becomes minus grad p. Okay. There will also be a rho here. Okay. So this then this becomes your momentum conservation equation. Okay. This equation that we obtained, this momentum conservation equation gives you evolution of the velocities. Right? So we got density, we got velocity. Now, oh sorry. Now we will go to the energy part. So similarly in energy, we will say that how does energy changes? Energy changes because of work done. So this is the work energy theorem. So now we do a conservation of energy. So energy is what? Energy is half rho v square. So here I have to just write it again here. So if I write like this will be kinetic energy per unit volume, right? Now, if you add the internal energy to it, which is also per unit volume, then this is I'll just write it as some other symbol. So let's write epsilon times rho, actually rho e, let's say. So this is internal energy per unit volume. So we take the rho out, then this becomes half v square plus epsilon. In this case, now epsilon is energy per unit volume and mass, right? Like so the rho e has been taken out. So the unit of this epsilon will not be energy per unit volume, but also per unit mass, per unit volume per mass. So per centimeter cube per gram, and that is the quantity that like comes here, because this is very simple quantity that we can understand the its evolution or conservation in this box. So again, I'll just do the broad brush here. We'll say that how does the energy changes in this box? Energy changes because of the flux. So this, how does it travel? through the surfaces. And again, we'll do the Taylor expansions. We'll see the divergence here. Other term that comes here is because of the pressure work done by the pressure. So if you look at here, pressure times dS, this is the force, and force times velocity is the rate of work done, right? That is the energy, rate of change of energy. So this quantity, which is acting on the surface, so on every surface because of the pressure, normal pressure forces, then this can be written as this using Gauss's theorem. Any surface integral you can convert to volume integral. You can just write div of this quantity, and that goes here. So this is work done due to pressure, and this is the work done due to gravity. So you have gravity force, then rho times g will be the force per unit mass, sorry, per unit volume, and then there will be dot product with velocity will give you the total energy generated or work done by gravity per unit volume. And that is what is goes here. And these two has to be equal because we are assuming that the energy changes only because of the pressure force and gravity. Suppose if you want to add thermal conduction or radiation or neutrino radiation, then you can just keep adding and your equation will become more complex. But we are assuming here a very simple case. Okay, so what this gives us these sets of equations. And somebody asked to give some references. So where I'm teaching for this from. So as I said, Padmanabhan is one good reference, but also you can consult Thorne and Blandford. This is one reference, and then also Mihala's book on radiation hydrodynamics, but it discusses fluid dynamics in general. Okay, so now we come to this set of equations, and now you can see that the g here, gravitational force, that is or acceleration due to gravity, that goes into the momentum equation. This is not a constant. This is a most crucial difference between fluid that flows on the Earth and the astrophysics, or in the astrophysical systems. Like what happens is in astrophysics, if you consider a star, then one part of the star is attracting gravitationally the other parts of the star and every other part, right? So this mutual gravitation is very small in fluid flows on Earth, right? If you are studying fluid in your bucket or something, then the mutual gravitation is very small. So we assume that G is constant. But in astrophysical systems like stars, that cannot happen. So this has to be solved, or this has to be obtained from the density distribution. And for that purpose, we write G as a gradient of potentials, which everybody knows. But then this potential has to be solved using this Poisson equation. There are some questions. Books in the PDF form, we have to consult libraries. I'm sure nowadays there are e-copies available. There are many. I think the easiest way is for you to go to Internet Archive, make a free account, and you can loan any book from there and read it. And then after you read, you can return it. So this is all completely online and free of cost. So you can do that on Internet Archive. Yeah, I'll share the presentation. Sure. Book name and all I'll give. I'll send all this. So let's just everything I'll give you. So you have to just focus on the physics part that we are discussing. So now these sets of variables, you have a density, you have three velocities, ux, uy, uz, and then you also have potential and pressure, right? Pressure and E energy. So how many variables we have? 1, 2, 3, 4, 5, 6, 7. We have 7 variables. This is one equation. These are 3 equations. This is one. This is one. So how many equations? We have 5. So 7 variables, 5 equations. So we need some more, right? Like no, this is 6. Right. So 7 variable and 6 equations. So we need one more equation to connect, and that equation is supplied by what we call the equation of state. Okay. So if you know P as a function of energy density and density, or for example, density and temperature, or density and entropy. It can be written in many equivalent ways. But if you know the equation of state, then now you can solve all these sets of equations simultaneously. Okay. So now you should pause and appreciate that this set of equations govern everything from a star formation to a structure of a star, even interstellar medium gas or expanding gas from when the star reaches its late period, or even evolution of the supernova ejecta through the galaxies. Everything is governed by these sets of equations. What changes from one place to another is just density. In a star, this density will be 1 to 2 gram per centimeter cube. In the dense case, for example, Earth, this density will be much higher. The velocities in the case of stars will be of order of I don't know, 10 kilometer per second, something like that, or maybe 100 kilometer per second. In the case of Earth, you can even use these equations to describe Earth's atmosphere. So in Earth's atmosphere, these velocities will be very small, density will be another like gas, pressures will be different. So and equation of state will be different. So these things only differ, but these same sets of equations describe all of these systems. So, I'll insist on for you to look at discussions in these books on Blandford and Mihalas and all this, to or other papers where you can see how these equations are solved in these different systems and then obtain a solution. So I'll give few examples. So let's say we are looking at steady state. So del T is 0. So if del T is 0, then you can already see that only this term will survive. This part becomes 0. So only this will be there. So now if you can write it as div of rho u equal to 0. Now we can write it, we can expand this part as rho div u plus u dot grad rho. Now suppose if you imagine that fluid is incompressible, then this becomes 0, then you get u grad rho equal to 0. That means that the velocity direction of the velocity fluid flow and gradient of the density are perpendicular to each other, right? The dot product is 0. So this is one consequence. Now suppose you say that there is no motion, so velocities are 0. So in that case, if you have to solve the momentum equation, then these velocities will become 0. So this whole term on the left hand side will be 0. So this terms will be 0. This del T is also already 0. So now you are left with only these two terms. So you will say that, oh, everything is gone, so it is very trivial. But actually this describes our atmosphere. So if you just do grad P equal to rho g, so this is the fluid dynamic that you studied in class 12th. Okay, that a fluid is static, filled in a tank or in the ocean, and how does the pressure changes with respect to the space or with respect to height. So this thing now you can write it, you can write down as del P dx as is this as this equation. You say only I want to understand the variation of uh, pressure as a function of height. This is the Earth, and you have this is the atmosphere on top of the Earth. So how it changes? So you introduce z variable as a convenient variable, and then if g is constant, then you can integrate it, and you get p equal to rho gh, p naught plus rho gh. So this you remember. Everybody remembers, I hope. Now suppose g is not constant. This has some variation with respect to z, which you already know what I'm talking about. Gm over r square. And if you plug this back here, then how does pressure changes then? What is the equation of pressure change with respect to the height? So there are some exercises here I've given to do, which I will give you later. Okay. So now we will quickly now go to the construction of stars. So first thing that we want to do again, so at a very simple level, what is a star? A star is something where in our modeling, we say that, okay, let's imagine a star where there is no velocity or very small velocity and nothing is changing with respect to time. So now you will come up with the same equation, right? This one, that velocities are gone, time derivative is also gone. So that means you have to solve exactly this equation for star. So how do we solve this equation? So first thing that we do here is this. We say that the del T is 0 and del R terms is also 0. Then, so this was the continuity equation. So the both are gone. Fine. Now, if you come to the momentum conservation equation, and also we do this in a spherical coordinate system, then you reach to this point where G part, here the acceleration due to gravity is now replaced with gradient of potential. Okay. So now if you apply this part, there's a del by dr, but since it is spherically symmetric, then this will become dy dr because there is no other variable. So then this comes out to be your dp dr will be just rho times grad of potential, which in turns can be written as this. Okay. So now your equation of stellar structure is basically dp dr equal to minus rho gmr at that point by r square and minus rho rgr. And this can also be written like this. Now, if you go to the next part, then we want to also do the mass conservation. So that is simply this quantity that at a distance of r, you made a spherical shell of dr. Then the total volume of this spherical shell will be 4 pi r square dr. And then multiplied by density at that location will give you the mass of that shell. So then this gives you the equation, which is looks like this. So dm over dr equal to 4 pi r square rho r. Okay. And this, of course, comes with equation of state to complete the model. So now what we do, we say that, okay, this set of equations, dm over dr, dp over dr, this set of equation, actually I'll just remove this part. I'll come to this later. So I'm already reaching 1.5 hours. I'll take maybe 5 more minutes, maybe 10 more minutes to come to the computation part and connect all the things that we discussed today. So now we have these sets of equation along with the equation of state, right? So I'll just write this down. This equation will be P equal to P of rho. Okay. So now you can say that actually you can solve this equation. This is, you have just mass and P, but how do you actually do it? How do you plan on actually solving this equation? So for this, we go to numerical part. So what we do, we first construct a small shell. Actually, I have a nicer figure than this. Okay. Yes. I hope this is visible to everyone. So see what I'm doing here. I will start with center. So I will make a small r. We call it delta r because I'm going to make every shell with delta r. Okay, these are all delta r, and so on. So I'll just make this, and since it is one dimensional, so on the code, if you have to store this, you'll just store it as a linear array, right? So first you will make these boxes. So this is your first box. This shell is your second box. Then this shell is one box like this. So now for each box, you'll make an array in computer. In a program, you'll make an array 1, 2, 3, 4, and so on. Okay, and each of them will have what quantities? So each of them will have some mass, density, right? Corresponding to each of them, you'll have some density. You'll also have some temperature for each point that we are not discussing right now. But so you'll also have some radii for this. So first one that you assumed, this delta r, what will the volume of it? 4 by 3 pi delta r cube, right? That is the volume of this small shell, and we'll multiply with the density at the center. So this gives you the M1, right? So this goes into there. So this pipeline is basically described here that first we assume the central density and this small r, and that gives you the mass 4 pi r1 cube rho c. Now we know this equation dm over dr. how mass is changing. So what m2 minus mc by delta r, this will be 4 pi r square rho c, right? This is what we are seeing here. I hope you can see. I'm just plugging this here. I'm just discretizing this. This part is called discretization. Okay. d over dr is written in discretized form. So now, knowing all these quantity, you know this, you know all this. So now you can calculate m2. Similarly, then you calculate m3, and you just keep calculating. You just keep hopping, and you keep integrating up to what point, right? So, and similarly, you integrate pressure. You have pressure because you know you assume rho c, so you equation of state, you calculate the PC, and then you have equation for dpdr, which is discretized here. Right hand side is goes here, and then you calculate the pressure, and then goes to next, and so on. And this is how you just keep integrating, and then you reach the surface. So, what is surface? Surface is the place which has zero pressure. Okay, outside the surface there is no gas, so pressure will be zero. And this is the condition you will use to find the radius of the star. Okay, so this is the method, and so now I'll directly come to the useful part. These things I didn't get time to discuss, but okay, I just want to I'll give you this part where the main codes and discussions are given. But this is for neutron star, but same code can be used to discuss that. So you have to go to this website. I will send this, so don't worry about link and all. So you have to go to this website on this GitHub page, and there is a Python notebook where these equations are solved. Okay, so all you have to do is this is solved for more complex problems. So what you have to do, you have to remove this part. You have to remove this part from the equations, from the code, and only use these part to make a star. Okay, so this is this is something that you can play with, and you can put these things for sun equation state and central densities, and then you can see, can you construct a star. Now this the theory of it, this is for general relativistic. So if you're interested, this is the link where you can go and check, but I will not recommend that. I will just say that within the purview of the discussion in this first half, essentially the first thing that you should do is this: just go to this equation page and then remove these parts and then solve for the stellar structure equation. That is what will be done here. Okay, so I think that is all for now for this. And next section we will just discuss. Maybe we can discuss this a little bit more. The radiation pressure to complete the stellar structure, and then we'll come to some binary or n-body system. So any question? There was one question, surface pressure, is this an ideal assumption? No, it's not an ideal assumption. It's just, I mean, in some sense, yes, because the outside star is not completely empty. Pressure is not exactly zero, but it's very, very less. It's orders of magnitude smaller than just inside the star. So that works roughly okay. But you're right that if you want to find out the very precise modeling of the, or you want to do very precise modeling of the star, then you have to be careful that what pressure we are talking about and how the pressure goes to zero. That becomes very important. Any other questions?
No poll right
Hmm.
now. Somebody asked, so in the next session we will have.
Okay. There is question, sir, will there be any polls? Sorry, I didn't design any.
Okay.
Yeah, I didn't design this time. But yeah, if you have any questions, you can do. Yeah.
Okay. Yeah, so I think so. Some students have already asked questions during the session. If
Yeah.
there are no more questions, we will break now, and we will meet again at 11 a.m.
At 11. Okay,
Yeah.
sounds good.
Yeah.
Okay, thank you.
Yeah.
See you again.
Yes, sir.
Yes. Okay. Please, Dr. Kashyap, you can start now.
Okay, sounds good. Screen. Just give me 2 minutes.
Yes, sure.
Yeah, so I'll upload some sections already. Just okay. So probably we can do some coding exercises if students are up to it. So let's go to the that repository, and then I'm assuming that everybody here knows how to run Jupyter Notebook, right? We saw that. Okay, maybe I can create a poll. Maybe. No.
Yes, sir. The two days we have worked on that,
Okay. So Jupyter
and
Notebook. Okay. So yeah.
so
So I'll just
either they are
assume.
working on Jupyter Notebook or they are working
Mm.
on Google Colab.
Oh, okay. Then great. Okay. So probably they can directly also do this. Okay. So what I'll do, I'll start. So I'll share this. Wait, just wait. Okay. So I'm sharing a screen of Jupyter Notebook. Okay. I hope everybody can see my Jupyter Notebook. Okay. So I have opened my TOB notebook. What I will do, I will make copy of it first. And I'll just rename it to. Let me know if the fonts are very small or things like that.
Sir, if you can close the sidebar, that will be useful.
Side messages.
No, if you can close the sidebar. Uh,
Oh yeah, okay. Actually, I'm working on the sidebar, so I wanted to,
okay.
but okay. TOV MS. So I'll just call TOV MS main sequence star. I'll open that. Oh, not here. So there are some questions on asymmetry of star. I'll come to that. That is not relevant for this discussion, so we'll come to this later. Okay, now it should be better. Actually, let's put this also. So this must be better, right? Okay, so first. Trying to find out that. Yes. So it's not marked here. Here it is marked. Okay. So this is for so I'm just first going to show you the final output that you're supposed to see, and then we'll go through the code to see that how it is produced. So this is uh, like one is just energy density with respect to density. So this is a plot of equation of a state. Okay, so just like PV equal to nRT, right, or P equal to NKT, capital NKT. This that equation is state for ideal case that if you plot the pressure as a function of temperature, then what you will get. So this is just an example. This is a equation of state of a neutron star. This is not normal star, but uh, okay, yeah, I should share the link to the repository. Yes, you do that. Wait, that code. I find out where did that go. Okay, I just pasted the link to the repository. And okay, you can still see my Jupyter notebook, right? Okay. So I just copied this TOV uh, dot IPyNB. That was this notebook. I just copied it and made TOV main sequence. And so right now I was showing you. Yeah, so this is the equation of state graph that we make just for not this one, sorry. This one is this equation of state graph. And then some derivatives of that equation of state. So dp d rho, this is pressure as a function of density. So that derivative is plotted and that gives you gamma, not derivative directly, but some function of it. And these things are plotted here. Now, this is equation of states. I'm just trying to find out the, yes, here. Now here, what I'm plotting is a structure of a star. Okay. Uh, let's go to some higher density. Yes. So for example, look at these two examples. here I'm choosing some central density, central energy density, and then doing an integration to find the radius of the star. So this is one dimensional. So what will happen? You will have radius on the x-axis. So for each point of radius, you will have a pressure. So that is what is plotted in blue line. So pressure, as you can see, pressure is nearly constant for large section of a large part of the star. So radius here is given in centimeter, pressure is in dyne per uh, centimeter square. Okay, so there is a request to discuss the code. So what we are doing here is that this code constructs a neutron star. Okay, so this is a code to construct a neutron star, much more complex than what we discussed. We discussed a star using Newtonian gravitation, so this is doing more complex, but it is very similar. The one other link that I posted there on the website, that one also I'll post actually. So what happened? So, in the June, sorry, something happened. Okay. Okay, so you can see my page. Okay. So you remember the stellar structure that we discussed, right? So there, what was the equation? Equations were dmdr, dpdr. These two things that I studied, right? Like how mass changes with respect to radius and how pressure changes with respect to radius. And to solve these two equations, since there are three variables, mass, rho, and p, we also need p as a function of rho, equation of state, and then we can solve it. So similarly here, this is the structure of neutron star. So this comes from by solving Einstein's equation, but not surprisingly enough, the equations are very similar. It is one dimensional, spherically symmetric. That is our assumption. But there are some extra terms like these terms here and all the terms in the bracket in the dpdr term. So what we're going to do, we will take this code, we will remove all this part, and this part, and I will use a different equation of state than the one that is used in the code, and we'll construct a normal main sequence star. Okay, it will turn out to be. We'll see that what are the components here that is important. So this is what we'll do. I hope that is clear. Okay, and then so we'll go to the writer notebook. So once you run the code, then you will get a structure of stars like this. So pressure is function of radius will be plotted, and then mass, cumulative mass as a function of radius. So as you can see that uh, the mass reaches a constant value. So after certain radius value, this becomes constant. That means mass is not changing. It is the place where you have largely very low density material, so it is not contributing to the star mass. And the other two quantities we don't have to worry about now, but mainly this pressure is a function of radius and mass is a function of radius. We obtain by solving a differential equation which is given in pressure and mass. Okay, so this is what is done here. So actually this is done in TOV enthalpy. So sorry about that. Let's make a copy of TOV underscore enthalpy. Okay. So we'll make a copy of this. Just delete this. Okay, now okay. So first, here what is being done is that it takes the TOV. So start the question. Why pressure is constant here? Yeah, so that is specific to neutron stars, so we don't have to worry about that particular problem. We are working on different problem, but pressure is largely constant because it's high density material and pressure changes very little in with respect to density. So okay, so here there is a library TOV-lib. What does that look like? Let's see that. TOV-lib here. So here what I'm doing, I'm importing all the major packages, which is all of these are freely available. There is a one file, my constants, that const, which contains all the constants. So that is given here in this file. All the constants values in different MKS and CGS units are given. And in the TOV-lib, these different functions are defined. I just redefine them. Femtometer I define, and some other utilities. So forget about this part. Okay, so creating enthalpy table. So here, what we do, we first construct the equation of state. That is done here. So uh, not this part. Mm. Yeah, here. So first you have to give a key. So there are different matter properties that is possible in Tonstar. So that is given here. It is different. You just pass this key, and these functions will give you the equation of state at higher densities, and then this function creates the full density. For our purpose, we don't have to worry about this, so we can just simply delete this part or just comment it out. Okay. What we need is this one. So pressure array, we have to assume, or you assume density array and calculate pressure array. So comment this part. So rho. This is on different minutes. Okay. For the sake of simplicity, what we can do, we can start with this same constant undefined. So let's go. Let's first import this. Time. Let's remove this part. Let's run it again. Okay, so this ran. We got this. Now, class thing, we can hide this. We are not doing this. Okay. Some more questions. Yes, so questions are all answered. Mm. So once that is done, then we can go to enthalpy table, try to run it. Okay, so it is running. Okay, so first remove all this part. This part, actually, it's better to just hide it. Okay. I hope you guys are faster than me in running the notebook. Okay, so just delete this, make it simple, make it simple. Okay, so first thing is we are going to import tovlib. So there are a lot of functions there, and then we do scipy integrate, and we import all these functions, and then we go to create enthalpy table, and we just run it. You should just do shift enter. It should run and give you this. Okay. So what it does, it used the equation of state table to construct these plots. So one plot is simply reading the function, but there are other parts where it is calculated. Enthalpy is calculated from the this pressure as a function of energy density and gamma. Gamma is also calculated. Gamma stands for uh, polytopic index of equation of state, which is not important right now. It's just derivative related to the derivative of the equation. Okay, so any question? Okay. So now after this, then we go to the construction of a star. So we know that what the equation of state looked like. This is given to us. Okay. So for example, if you have sun or normal star, what is the equation of state of that? And then you'll find that the material or the particles which exerts pressure and against gravity and keeps the star stable against gravity is basically photons. Photons are exerting pressure, and that pressure has a very specific type of equation of state, and that you can put in there. I'm just showing you this by running this notebook that will solve. Okay, so this part we don't need. I think what we can do is so here three different equation of states have been plotted in this plot, so that also you can practice how different equations looks like. Okay. These are some older experiments. What I'll do, I will clean it up and then upload and send you guys a notification that it is cleaned and you can put. Okay, now we are here. So we are construct a star. So now we'll run. I'm not sure how much time it will take, but let's see. POV not defined. I see. Okay, now I see what I mean. Let's define this. Okay, now it's working completely fine. And it's quite fast as well. So, okay, so this section, so whatever is available, so I hope everybody has their notebook open. So what you have to do, is, okay, people, yeah, code link, everything is given. Any questions other than this? Or please use dark theme mode. Okay, that is very specific request. Not sure where that will come from. I mean, I guess sharing. Okay, I mean, you can see this. Let's just go ahead. Okay, so only this section, this TOL section, and then settings, and then theme. I see. Okay, so brighter dark. Is it better?
Yes, the students prefer this because for a long time they are on the screen.
Oh, yeah, sure. Okay, one question is where can I access this specific notebook? So this notebook is called TOV_enthalpy. You make a copy of it. Okay.
Sir, I'm also requesting you, already sent you a message. If you can upload this notebook or link on the classroom.
Yes, I'll do that. Yes, I will do that. Uh, uh, I'll take actually 1 minute to do that. I'll just after explaining this, I will do that.
No, you can do that after the session.
Okay.
so that people can work on the assignments.
Yeah, definitely. Yes. Okay. So first thing is like here we create the enthalpy table starting from the equation of state, which is already given here. So here I will say what modification you have to make. And then after this, we define a class. This is called TOV. And this is the part where the differential equations are defined. So now I hope you can see there dPdr, dmdr, and dypdr. Right? Three things are given here like this, right? So here, if you look at the Newtonian equation of motion, then you'll find that it is only a small part of it which is going to survive. So for example, this is fine if you just replace E then with the rho, okay, then this will be okay. You don't have to include these two, so you can remove these two parts. So now, but then also you have to modify this function that you don't have to return these two. You only need dpdr and dmdr. For dpdr, all the terms with c square can be removed, so you'll be left with g, and then E density will become rho, and then m, and divided by this r here, divided by r square. So this is written in some cryptic form, but it's the same equation that I discussed, that I showed you with the TUV, except the other terms in the bracket. So you have to remove these two, then you have to keep only dmdr and dpdr and return only these two. Okay, and then remove this part. So where this is going, this is the setting up the TOV equation. Then we come to TOV solve. Okay, so what TOV solve does, it starts with an array of central densities or central pressure, and then starts integrating for each of those choices. Okay, so for example, Sun is a star with one solar mass. Now you want to construct two solar mass Sun, or two solar mass star. Then in that case, you have to start with a different higher central density, but everything else remain the same. Okay, that is, so we are constructing two stars which are made up of same material, but their central densities are different. So we'll start with different central densities, and that is what goes as input here. So you say that solve this star or construct this star with this central density, rho c. What is ED? Is TOV is a library in Python? Yes, it's all in Python. And Eden is the energy density, which for Newtonian case will be simply mass density. So Eden is just a rho. So you don't have to define two different. You can just remove Eden from the code and just keep only rho. So and then you have to define dpdr here. It will be just, this will become rho. This will also become rho. Okay. So this is the part, and then there is a question of find surface, and I'll come to that. That like, what does it mean to find surface of star? Basically, surface of the star is the point at which, or the radius at which the pressure becomes zero. So uh, so there is a special function for that, and then there is a function called define mass radius, where we we do the TOV solution or stellar structure solution in this case, in your case, for different value of central densities, where central density is coming from an array, rho C's. This rho C's is constructed, is given to this function from when we use this. So remember, how do we use it? So first we construct an equation of state using this function, these two functions. And then we construct a Rossi array. This is our choice. Okay, we want to construct different types of stars, and n is the number of stars that you want to construct. So here I have n10, and these are some other quantities. And then I say that I want central densities between 2 times 10 to the 14 gram per centimeter cube to 5 times 10 per 15 gram per centimeter cube. This is the density of neutron stars, but for normal star, this will be actually 2 and 5 at max, I think. maybe it will be a bit higher. And then I construct the equation of state, and then for each value of the central density, I will construct the star. What does it mean to construct the star? I will call this function TOV solve for this equation of state LF2, and then this will give me the radius, pressure, and mass arrays. So I will get all these arrays, and then I will plot radius versus pressure, radius versus mass, where mass is divided by the solar mass. Also, pip install TOV will not work because it's on the GitHub repository. What I can do, I can try to make it pip installable, but then what you want to do here, you want to go through the code and read, but so then you have to ultimately copy the Git repository and then install it from there or run from there. So, so that's a good question. What is self in this class? So self is basically the class itself. So whenever, basically what is a class? Class is a collection of functions and data types, right? So here the most basic the like structure of class looks like this. You have a class and then you have a default function, one compulsory function that is called init, and you basically self you pass because if inside any function you can use other functions. So for example, you can use TOV inside calc formality, or you can use TOV solve inside TOV like that. So you refer them as self dot. So for example, here self dot rad low is actually coming from here, which you use to define the class. Okay. Okay. N in this case here, N represents how many stars you want to construct. So each star is characterized by what? Different central densities, right? So you take each star for different central densities and you construct the star means, construction of star means that you get arrays, radius array, pressure array, mass array, and so on. And for your case, you only need 3. So you have to modify these functions to make it only for 3. Okay. And in the end, you have to plot. You have to plot that what, for example, we are going to focus on our sun. So for example, our sun, how does the pressure changes with respect to radius in our sun? And this is a mass, this is cumulative mass. So how does the mass, total mass changes? So by the time it will radius, it will reach the surface of the star, the mass should be 1 solar mass, for example, in your case. This is neutron star, so there's a different case. And what is interesting is to observe in this case is that how pressure changes. So you'll find that this will also be the case for sun, but not for so long. In the interior part, pressure will be slightly constant, but then it drops in some fashion. So you'll see that. And then after this, since you did it for many central densities, for example, you can see here that this is central density 2.45, this is 3.5, this is 5. So for each central density, you are getting a radius, right? For example, in this case, what is the radius? This is about 10 to the power few times 10 to the power 5 for the blue one, right? Here, the radius will be slightly different. So for and total mass will be different, right? This goes to 1.6. This here goes to this also goes to 1.6. This goes to 1.2. This goes to 0.6 solar mass, right? So all of these stars, since we are starting with different central densities, they have different mass and different radii. So you just take all these points and you put them in single plot. On y-axis mass, on x-axis radius. So you get a point like this. So with 10 points, it looks very broken, but this is your mass radius curve. Okay. Any questions? So is this code specific to construct different stars which differs only central densities? Yes, but you also have to change equation of state if you want to construct a star other than neutron star. What is the region of sudden pressure drop? This is just comes out of the your basically stellar structure equations. You will not find this thing everywhere, but the other thing is to notice is that it might feel like large range, but it's not. This radius is in meters, I think. No, centimeters. This is in centimeter. 10 to the power 5 centimeter is a kilometer. So it is like few tens of kilometer. This is neutron star is. So you say that this is 10 to the minus 3 centimeter. This is so uh, up to a kilometer, slightly smaller than kilometer, neutron star has constant pressure, which is only 10th part of the neutron star, by the way. So in that sense, it is not that it's constant for a long time. So okay. And so this is your mass radius. Yeah.
So
Hello?
what is the meaning of two different masses or two different radii for the same mass?
Yeah. So this is for neutron star. This is a unique type case. This is also not the case for white dwarf. For what neutron stars, it can happen that uh, two neutron star with very different masses have same radii. It's just that what it says is that when neutron star becomes heavier, then the internal matter changes, its equation of state changes, and then it brings the star to the same radius. But the matter is changed. This is not the case for main sequence stars or white dwarfs, where it could be higher density, but the equation of state matter changes by composition a little bit, but the equation of state doesn't change a lot. So it will have different radii. So this is roughly people explain. Okay. We have money US for neutron star. How to choose one out of them? So that's a good question. This is an open question. So we just asked a very nice question, which is nobody knows. So we are still figuring out what is the correct equation state of neutron star. Okay, so I hope this was good. So now I'll go back to describing some other concepts regarding this, and then we'll go to study some binary stars and n-body systems. Okay, so first thing is about the equation of state. Let's see, where is that? Here, I will not go through the full radiation transfer equation, but I'll just simply describe another equation, which is that just like mass and density changes with respect to radius, temperature also changes with respect to radius. And it is the temperature gradient which actually supports against gravity through the photon pressure. And that equation is given by this set of equations here. Here everything is already known. In LR is the luminosity, at radius R, T is temperature. This particular quantity is called opacity. It is connected to absorption or emission of light from the matter. So light and matter interaction is encoded in this quantity called opacity. So this equation can also be added to the Schiller structure equation, and you can also plot in addition to mass and pressure, you can also plot the temperature with respect to radius. So you'll find that temperature is high at the core, but then it falls. And then in sun, very weird thing happens that at the corona again temperature increases. And that is still kind of puzzling to many people, but this is a bit complex. Okay. Uh, I'm trying to find out the equation state for the theoretical equation state. Sorry about that. Here. Okay, I'll send that thing later. Okay, so let's just focus on this part. So what do you get after making the model of stars? I'll just do brief description. So it turns out that uh, the the full description of the stars that we observe in the sky uh, uh, it requires a comparison with the full population, right? Because what we see is not just single star, but full population of stars, and they are generally plotted according to the luminosity and mass. And this plot in this 2D plane is called Hertzsprung Russell diagram, and a very modern and updated Russell diagram has been released by Gaia collaboration, who observed millions of stars in solar neighborhood, and this plot basically shows that uh, that our observations are still like in the same ballpark. The updated Hertzsprung-Russell diagram is very close to the older Russell diagram that has been observed on very small sample stars. So what is on the x-axis, you have this color, which is essentially reflection of the surface temperature. So we can just focus on this part. So on right, it becomes smaller. And on y-axis, we have luminosity. So with respect to the sun luminosity, so this is solar luminosity. So sun is about somewhere here. And then as it will evolve, then it will go towards up in this diagram. And then ultimately it will go there and then it'll come back to become white dwarf like this. So every star is born somewhere here in the main sequence, depending upon their masses, and they evolve and go through many different stages to become different things. So how do we get this understanding? Like how do we, from this modeling, how do we compare this? So we cannot see a single star evolving through millions of years because our age itself is very small. The whole humanity has very small time on Earth. So what do? We do a statistical comparison. So for that, what we need, just like I showed you in the code that we evolved 10 stars, right? But we need to evolve millions and billions of stars. And we will, after evolving, we will put them in this plot, a plot like this. And then we'll ask the question that does it match with the observation? And not only statistical, but also every individual star that we see, we can also take their model, their surface temperature, spectra, and everything, and we can model and compare with our model, uh, apples to apples, like what is their luminosity and mass and radii. And such detailed comparison requires numerical calculation, and numerical calculation actually gives us this scaling that the luminosity of a star basically scales with mass as a function power of 3. This is again taken from Anu Padmanabhan's book, volume 2, uh, but you can find it in many different places. This is called theoretical astrophysics. Let's write this down. Okay. So this has so for
A
yeah,
question.
sorry.
Sorry. No, for these very low mass stars, where the luminosity mass relation is different than for high mass stars. Now, has
Uh-huh.
it been verified with the latest Gaia data? Because now we have reached very low mass and large number of them.
That's a very good question. I think it must be because its horizon is higher, so even low luminosity stars must have been observed very large in numbers. So I mean, I don't remember any paper coming out with any surprises. Uh, but I can't say for sure. Yeah, very good question. This could be a kind of open problem, and somebody can work it out. Okay, the question is BP minus RP color. What is that? And do you observe the color of the star from a space telescope too? Yes, of course. I mean, wherever if you have filters, proper filters, then you can observe color. So well, I'll just briefly describe the color. Oh, sorry. So color is essentially, so you remember that whenever you see electromagnetic radiation, it has some distribution in wavelength, right? So now the area under the curve in some range is what is observed by some telescope, some filter. So let's say we call this B band, and then we call this uh, let's say R band, like this. So and they can have different profiles. So what do we do? So if this is so Planck function, we integrate, let's say lambda. So we integrate over wavelength, and if you integrate from in B band, so then you get some energy, that what is the total energy coming out from the B, and then you can integrate the same function in R band, and the ratio of these two essentially gives you color. So suppose this number is very large, then what do you mean? That star will look like blue, right? Because most of the energy is coming in the blue band here. So it will look blue. So actually, the actual spectrum would be something like this. Okay. So these filters, what they do, they filters basically they remove other parts of the light. So you take a filter and you put it in front of a star, it will just block out all the light. It will only allow this band. Okay. So the difference of magnitude, which is magnitude is what? Magnitude is log of luminosity in some band. So this is the magnitude in that band. And so the difference of magnitude, let's say MB minus MR, is equal to this guy here, ratio of luminosities in energy in two different filters, and that basically gives you color. So that's the intuitive explanation. Exact calculation you can do, it's just same thing. Okay, so this is the part where what I will recommend is to go through like some self project kind of mission. Everybody should go and install Mesa. Mesa is the most complete stellar model code currently. It is one-dimensional, so it makes spherical stars. But on top of it, it also does some little bit of trick to consider 2D motions, for example, rotation and all. But this is one of the most complete. It contains nuclear reactions, radiation pressure, and all those things. So what you can do, you can run Mesa even online. So what you should do, you go install Mesa or run online and play with the masses. So start with different solar mass and then see how it evolves in HR diagram, and see like how, if you can run it on your laptop, then you can run 10,000 or thousands of stars and then plot them on HR diagram. So this is and suppose if you come up with some research problem and you want to play with that, then also you can do with Mesa. Mesa is a very capable code. It's modern and research grade. So yeah, starting from study to understand the stellar structure to the point of doing research, the single code can help you. So here you can do all these things. You can also study stellar populations and then see how it works. So this was one thing. Okay, so now any questions so far? Actually, I'll just stop here.
Shall we use 2 minutes for a poll? Just a small feedback poll.
Yes, please. Yeah, if I'm going slow, fast, all this, yeah, I think we can do that. Yes, please. Do you want me to construct poll or you're done? Okay, nice.
I launched the poll. Let everyone.
Okay. Okay. Question is, can MESA be used for possibly planetary systems? So that's a good question. For n-body systems mutually attracting each other, there are different code. MESA is evolving only one star at a time. So two stars together attracting each other and influencing each other with respect to different forces, radiation and all. Those things are not modeled in MESA. So you have to go to some n-body systems. I have one reference code that you can start with, but uh, you have to basically go through them on your own. So
Okay, I'll end the poll in 10 seconds.
sounds good. Wait, just wait.
Yeah, the
Okay,
poll is
that's very
ended.
enlightening. Paul is very enlightening. Coding dynamics on a task will be useful. Yes. You have to do right code and see results. So yes, a lot of people. I mean, generally, yes is a lot. Due to study. Um, it says, okay, sorry, I stopped sharing. Oh, should I share the result? Sorry, I should do that, right?
No problem.
Uh,
This is for us.
oh, okay.
So that's fine. We can continue with the session.
Hmm. Just- can I get can I somehow get this result like as a
I will
as a
share.
offline?
I,
Or
yes, I will share
you
this
will
on.
have the like
No, we
full
will have
result.
this. We will have the full result, and we will
Okay,
share
okay.
that with you on email.
Okay, thank you. Yeah, that will be very useful. Thank you. Okay. Yeah, so on MESA, a lot of questions there. Is there an alternative for MESA for n body? Yes, there are. So let's go there. But first, let's look at the some theory behind it. We don't have much time, so we'll just go that. Okay. Okay, so one few simple exercises I want you to do that goes very long way in astrophysics in general is to understand the mass function of stars. Okay. Here I'm talking about initial mass function, but in general, like what we understand is mass function in general, initial or final or evolution of it. So what is mass function? Mass function is the number of stars as a function of their masses. So how many stars are of solar mass and around? How many stars are there for 10 solar mass or 100 solar mass and so on? What does this function look like? Does this function look like this? Or it looks like this? What does this function look like? That is the main question that we want to ask. And especially we are interested in initial condition that when the star forms or lots of stars form together, in that case, what is this function? Because if you're thinking from the modeling lens or modeling perspective, and you want to compare the stars that you observe in the sky, you should remember that these stars are not born now. Some of them have been born like for they were born like billions of years ago. So that means all the stars that were born at that time are not now. Stars which are heavy, they evolve faster, so they are they disappear. So that means we have to uh, somehow backtrack or reverse the observation of the sky and then check that how what was the initial, but that we can't do, right? So to compare with the observation, we have to assume some initial distribution, and then we have to evolve according to the stellar structure evolution, and then we have to check whether that matches with current observation or not. And we will evolve them for billions of years, for 10 billion years, at least the age of the universe, right? So it turns out that direct observations in globular cluster or young stellar galaxies, this kind of mass function is observed. Okay, what it says is that there's a lot of stars near solar mass. Most of the stars live there, and this is on log scale, by the way. So on log scale, this is straight line. That means it's a power law. That means the number of stars around one solar mass is a lot more compared to higher mass. And this is the exercise that we want to do. Through observational surveys and all, we have found that this exponent is about minus 2.35. This is very old from salpeter. It's called salpeter initial mass function around during 50s, but there are also new ones. And this exponent is something that is not fully fixed. We observe something and then we assume something around 2 to 3. It could be, or I think 2.2, 2.5. That is the range currently. But let's just assume this and then try to find out that uh, what are the masses of in a given range. So what you have to do, you have to integrate this function. You have to take this here and integrate it in a range. So you have to put some mass limits. So you have to do m low to m high. Okay. So now, and then if I say that white dwarf will be formed if the initial mass of the star is between 0.5 to 8 solar mass. Neutron star forms if the mass of the star is 8 to 15 and 15 to larger than 15, for example. Then it forms black hole. Then what you have to do here, you have to integrate this function in these different ranges, and then find out that how many white dwarfs form, how many neutron stars form, how many black holes form. Assuming that all the stars have evolved up to infinity time, like end of the life, and then, or just 10 billion years, for example, and then what are their relative proportion? You will see some surprises. And then these are the numbers. So here we are calculating the numbers of the white dwarf. But the white dwarf and neutron star black holes masses are different. So then you have to calculate in the next subpart is that what are the masses of the white dwarf? What is the total mass that will be left in white dwarfs compared to what is the total mass that is left in neutron star black hole? And we'll find that, since small mass stars are a lot in number, then most of the end states of the stellar evolution will be white dwarfs. It will not be surprising in that sense if you have already thought about it. Yeah, so this is the extension of that question. So I will pass this. Now, this is a very crucial information. So learning lesson here in this part is simply that there's a lot of low mass stars, and most of the stars are going to become white dwarf. So this just says the importance of white dwarfs in a stellar evolution. Okay, and so why we are interested in white dwarfs or neutron stars, and the final frontier or latest frontier is the generation of gravitational waves. And gravitational waves require massive compact object. So a lot of mass stuffed into very small volume, rotating or accelerating in some region. These are the ones that can produce gravitational waves. And the easiest candidate to produce such waves in universe are these compact objects. So now what we do, we construct all possible binaries of these systems. So, and these, it was not speculated, it was speculated, but it was not worked out before uh, in full detail that how these binaries form. And these also lie in some of the open questions in current astrophysics, that how these binaries form. What are the detailed mechanism through which they form? Are they forming through mainstream stellar evolution, or they're forming through captures? These are the questions that we don't know. And to do this, again, we do the simulation, but this time we do a slightly different types of simulation. So here, for example, this is just a schematic diagram from one book by Physio Pandistar from Vandenhuvel. And it just describes that suppose you have initial mass function which looks like this, and as the binary will evolve, or even single star will evolve, they will go to one bin to another bin, right? They'll just keep hopping from here to here because they are losing masses. And in the finally at the end, so we'll start with two stars. They will go through many different stages, and they can end up with, for example, here white dwarf neutron star, and other components. So this kind of simulation can also be done, and this is something that I will also just show you briefly online. Okay, so now I will stop sharing and I'll share the screen here. Okay, I hope you can see. You can see updated BSc. Okay. So this I generally show this code because this is simplest for pedagogical purpose, for understanding things. So this is developed by Professor Hurley. This is one of the first. He was one of the first person to actually write down a code to uh, do the stellar evolution on large scales, and also binary stellar evolution on large scales. And his codes are still available. These are very simple C code you can download and install. Earlier, there was facility to run these stars on the website itself. Even now, it is there. But when you click on evolve star, it just says you can't evolve. So my guess is that these codes, like those backend servers, have stopped working. So what is these things here? You have three different types of codes. So this is for single stellar evolution, and for, as I said, single stellar evolution, Mesa is the best code. And just a structure of star you want to understand, that's the Python code I shared. Uh, and the binary evolution, you can understand using this code, that if you start with a given initial mass, then what happens to it, what kind of star it becomes. And the whole theory is given in this paper, uh, which I briefly touched upon. And there is also a code of n-body. I did also find one n-body code which is in Python. So I'll paste this. I'll paste actually both. Just give me 1 minute. This is, okay, so I'll be ending the class in few minutes. No, not few minutes. 12:30, right? Okay. Yeah, 12:30. Okay, so I pasted the link to the code. I'm especially excited about this n-body. This is written by one researcher. He's at Princeton, and I found this very simple, the simplest n-body code that you can see, and we can just read it directly on the web page. And if you want, you can also run it. It uses only NumPy and Matplotlib, so nothing else. Okay, so what is done here? It just creates that movie, so you can also evolve binary star or triplet or n-body, anything. So first, it starts with number of particles, how many stars you have, and then current time simulation is equal to 0, and then at what time you want to stop it. Then each of them have same mass. This is given a position. All of the masses are given position and velocities at the initial time. Then convert to center of mass frame. These are all just tricks. If you choose, you can also do in some other reference frame. Now, first thing that is done is getting acceleration of all mass points. So mass array is passed to this function, and corresponding position is also passed to get the acceleration. And that is all you need, right? You don't need velocities because the gravitational force depends only on the position. So you only need position and mass. and then acceleration calculator. So let's look at this function, get acceleration, what it's doing. What it should do, it should be doing is it should calculate the gravitational force because of all other point particles, and then divided by the mass of the given particles. So basically calculate the potential, then take a gradient. That is another way that one can do. So this is the get acceleration function. What it's doing, it takes all the position, takes x, y, z coordinates, then calculates the particle separations, that rj minus ri. So between each of the particle with respect to each other. So it will be 2 by 2 or n by n matrix. And then in inverse r cube is calculated, and then with respect to the direction, that's why you did the r cube. And then acceleration in all these three directions, x, y, z, is calculated. Sorry. And that acceleration is passed on. So now how do we use acceleration? So we use the acceleration. So that's to actually, okay, so now first is here kinetic energy, but to calculate the, let's go to this part, yes, here. So I in range nt is the number of time steps. So for each time step, what you will do, you'll calculate the acceleration, multiply by dt, you get the increment in velocity, right? V equal to u plus at, you remember? So acceleration times delta t, that gives you the increment in velocity. Increment is already done. This is plus equal. So velocity first, data of velocity will be given. You will assume this. And then position will be what? Position will be x. Sorry, this thing, why is this happening? Yeah. So position will be what? Position will be position plus v dt. That is what is done here. And then update acceleration. Then acceleration again you update, and then velocity, and then you update time. You calculate the kinetic energy and potential energy and save it, and then you make a plot. Okay. At the end, what do you get? You get a figure like this. Okay. These are the 100 particles. What is done here? These, you see this dot, 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 dot. So basically for each point, the current position, their position at the time of this snapshot is given in the dark blue dot, and other previous maybe 20 or 30 points or 50 points have been plotted as light color blue. And at each point, these, since they are moving around each other in a full chaotic manner, they will have different velocities. So you will do half mv square for each one of them separately, add them. That will give you kinetic energy, and then you'll do gm over r, gm gm1 m2 over rij, and sum over all. So you'll get potential energy, and then you'll see that these are like plotted as a function of time. And this is essentially a simulation of, you can use binary star, or you can use triple star, or a globular cluster, or even galaxies. In principle, these are the equations, and this is how it is solved. Now comes the question of computational efficiency. Okay, that how many stars actually you can solve using this. And that turns out to be very difficult. Okay, so as you can imagine that for each star, you have to calculate the force because of every other star. So the total number of operation is n square, order of n square, right? So that means if you have to simulate 100 star, you have to do 10,000 simulations, 10,000 such calculations each time step. And if you have like 1,000 star, then it will be 1,000,000. So it grows very fast. And that is basically, and the number of stars that you want to simulate is order of billions. So even 1,000 or 10,000 is very difficult to do. So billions of stars doing n-body simulation is simply impractical. And that brings you to the domain of mathematical approximations and different methods to solve it. Okay, so that part I'm not going to discuss, but I'll just say that I'll just describe a beautiful problem that you can solve and enjoy using this Python code on the iPad. So just describe that. Okay, what line in the code gives that previous info of a star in the plot? Yeah, so previous info you have to save it. So I think if you look at the code, then what it is doing is it is doing a scatter plot. So plt.scatter x x y y. And then next is position 0, position 1. My guess is that one of these is the current position, other one uh is the is an array of previous positions, so x and y, and those are plotted in different color. So I guess this is color blue, so this is final position, and this upper one is the last few points. I hope that answers your question. Okay, sounds good. Okay, so this is complete description of any cluster of stars, okay, or any mutually gravitating system. Anything that you want to calculate, you can calculate from this. Okay? So for example, you are modeling a galaxy. So for each of these, you know their masses. So now since you know the stellar structure modeling now, then given masses, you can find out their luminosity. So that means now you can calculate luminosity of the whole galaxy, right? So let's just do that briefly. Uh, Calculation. Okay. Okay. So now suppose you have a galaxy. It looks like this, and you have all the stars here in this galaxy. And it turns out that most of the masses, because of which the stars move, is not the visible mass, it's the dark matter. So you have to also incorporate those things. But okay, so first thing you realize that if you do the double loop for I and then for J, and then you do G, Mi, Mj, Ri minus Rj square. If you do this kind of thing, then it is order of n square, so it's very expensive. Okay, so that we can't do. So, but if we could do that, then so we have all the stars. So what are the things that we can calculate? So we can calculate total mass. So Mi times Ni, right? Ith type of star has number Ni. So if you sum over all this, you'll get the total mass of the galaxy or cluster, right? So I'll just call it GC for globular cluster. Now, if I simply do luminosity of each type of ith type of star and multiply with their numbers and then sum over all, then you'll get the globular cluster luminosity, total luminosity, right? Similarly, you can do a lot of things. So for example, for each star, you have some spectrum like this. So now suppose each star is emitting some light in some band, let's say R band here. Then you can combine only the R band luminosity. And this will give you the R band luminosity of the globular cluster, okay? Suppose you want to calculate the root mean velocity square. So what you can do V square, Vi square, Mi, like this, you sum over all, then you divide by the total mass, okay, which is simply nothing but Mi. Here also you have to do Ni. And then you divide by the mass, and then you take the square root, okay? So for example, you get this, actually you can also remove the half part. So this you get something like energy averaged mean square velocity. Okay, so this is something that you also observe. Right, so when you make this model, you also observe this quantity for different global clusters, so you can now compare. So this is one thing you can do. This is like I'll just call it global properties of clusters. This is one thing. Another very interesting thing is also done here is to plot Poincare maps. This is at this point is just interesting, but and there are many different applications of it that I'm not going to discuss. So, for example, Poincare maps are actually maps of any dynamical system. Any set of discrete particles or where they are evolving in position or in some other space. So, what we do, suppose you have a pendulum which is rotating with theta. So we can describe this pendulum as a function of theta. So we'll say that as the time grows, this theta will become positive, negative, positive, negative like this, right? So this is the actual motion of pendulum in theta space. But we can also represent the pendulum as velocity and theta space, right? So let's just keep theta here. So what will happen at t equal to 0? Let's say t equal to 0 is here. So theta is some positive value, same value that it has here. But the velocity is what? Velocity will also be 0. So this is the correct part. When the pendulum will come to this part, this location, then the velocity will be maximum, theta will be 0, right? So then it will go like this. And vice versa, it will happen, right? Like this. So in theta v space also it looks like this. So now suppose if you have two particles going around each other in gravitational force, then if you go in the center of reference frame, then both particles can be represented as two angles, actually one angle, and they're both velocities, v1, v2, like this. So this is like three-dimensional space. So what you have to plot is just one section of it. So you have to say that theta equal to constant, and then just plot in v1, v2. So how does this changes? How does the velocity of these two stars going around each other changes if you fix the theta? So what this means is that uh, so in the center of reference frame, they will be just rotating around their center of mass. They'll go like something like this. So wait. This is the path. And sorry. Okay, my pen stopped working. Okay. So basically you have two stars going around each other. So you look at only same theta, but as it changes in time. So you'll find that this will also be a periodic motion, right? A binary star, whenever it comes back to its configuration, its velocity is same because it's periodic motion. So
Sir,
here also you'll find, sorry.
Yeah, so in Poincare map, we may also consider, taking that the theta value at particular time interval.
Yeah, time also you can fix.
So say
Generally
for
any.
example,
Uh-huh.
when you are talking about a cluster, so what
Hmm.
is that time interval? Because for different stars, it is going to be different period. So what is the time interval that one chooses?
So one just looks at that whenever that cluster of stars, so for example, we say that let's say uh, velocity of so we can always do 2D, right, maximum. So we say that we choose two stars, we say that there we only plot their velocities as a function of time. So for all time points, we'll just plot that, but we'll fix the velocity of other stars. So we'll say that uh, so okay, my pen is might be working now, so I'll just write it down. So essentially, what will happen in the so this is for single system, this is for binary. So we can just do for three first, and then we'll go for. So for example, for three body systems, again, we'll have three positions. So R1, R2, R3, and three velocities, V1, V2, V3, right? Vector. And we'll have a time series of this, right? For all of this. So we have an array of all of this. What we'll do, we'll say that let's fix this V1 velocity. So this V1, wherever this V1 is between, let's say 5 to 10, we take those sections and then we'll take the other velocities from the other arrays, and then we'll plot them as 2D. Okay, so we don't worry about others. We just say that whenever the V1 is between some range, suppose V1 is between 5 to 10 here, 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 and here. So then we take all these values from V2 and V3 and we just plot them. We just do a scatter plot of this. So it will look maybe something like this. It may look like very weird types of shapes can look something like this. Like this. So it just tells us that like as a dynamical system, as a system which is evolving in time, what are the patterns it has in the repetition? Because any body system beyond 2 is non-integrable through quadrature. That's a statement which means that we cannot integrate and get a nice analytical formula. So what we can do best is to understand the periodicities or some ways of their repetition, any 3-body or n-body systems. And Poincare map is one way to understand such systems. So in this exercise, what you can do, you can just take the Python code, run it, but plot these kind of velocity, the scatter plot in velocity space of different bodies. Then what you can do, you can take one star, make its mass heavier, so 10 solar mass, keep everyone else as 1 solar mass, and then do a Poincare map of 10 solar mass, for example. So this like few exercises, I will write it down in the notebook, the notes that I'll share, and then you can practice. So I think this was my final. I didn't get chance to prepare the basically potential theory of n-body systems, which is nothing but solving Poisson equation, but uh, the stellar structure that you have studied, that actually you can use to study that. Okay, so I'll stop here and take some questions. Okay, what is that constant angle between two stars? Okay, so yeah, so I'll just make this graph complete. So suppose this is binary star. Oh no. Yeah, so binary stars, how do they go around each other? Oh wait. No. So they rotate around each other and they make a common uh, line of separation, right? So if the star is here, it is here, then it will go through some point like this, right? If it is here, then it has to go again through this point, be here. So if you look at in this case, Poincare map will be, for example, that whenever the star come at this line, closest to each other, for example, or furthest to each other, what is their velocity? You'll find that it is same. It will always be same. So Poincare map in this case only would look like just a point, because every time it will come to same point, right? It will just keep coming. But if you take a 3-body system, it will be here and then slowly it will start going somewhere. Yeah. So this kind of visualizations you can do, and then yeah. So do we have to take theta as constant? Yes, because you have 3 variables. So how will you represent 3 variables in 2D space, right? The whole point is to understand higher dimensional data in lower resolution data. So there is one very good question: do we apply Maxwell-Boltzmann statistics on stars in the star clusters? That's a good point. Unfortunately, stellar clusters are not such a large number that we can do fluid approximation, and apply large number statistics. They are not 10 to the power 24. They are 10 to the power 8, sometimes 10 to the power 5. But they are sufficiently large that you can use a statistical method. So in that case, what we do, we say that we describe them as a distribution function. So we say f as a function of r, velocity, and time. And there is a function that describes a cluster. And then we look at how this function changes with time. And some of the methods that was developed by Maxwell and Boltzmann is used here. But Maxwell-Boltzmann distribution may not be observable in the stellar cluster. So that's a good question. Okay, I think there are no questions now. So some exercise on Poincare maps for n body. I will make it a bit nicer. So is it okay if I upload the notes maybe tomorrow? That
Yes, sir. Yes, yes.
I'll take some time to make it nice and
Sure.
informative, and then upload it. Maybe I'll do some modification in the code as well, so that, and upload on the classroom. So any questions they have, I'll can answer there directly.
Yes, sure.
Mm, mm. Okay. I hope everybody enjoyed at least uh, some part of it. And what is required here is like self motivation. You have to go out there on the internet, and you have to search uh, all possible types of literature and codes. Uh, Especially regarding computational physics, I'll say that uh, the current structure is such has developed so far ahead that writing a code to do any of these problems, for example, binary stellar or single stellar evolution, all from scratch, is similar to making a Hubble Space Telescope on your own. So what you want to do is not like make a telescope again, but just understand how that telescopes work, or in this case, how that code works. Any code on the internet, for example, Mesa, you should be able to read the code. You should be able to install, do some changes in the code. It could be even a print statement. So just install the code, run it, then put a print statement somewhere, and then run it again, and then see your print statement is coming or not. And then you go ahead and then change. You can change anything. You can change gravitational constant. Just change the Newton's constant value by 5%, and then see what happens to a global cluster. Does it collapse? Does it fly away? Is our solar system stable if our Newton's constant changes by 1 or 2%? This kind of question you should ask yourself, and then you should be able to answer just using the code. So and that is, I think, is a preferable way to in current era. And as far as simple code writing is concerned, like to understand the concepts, you can always use Python. Python is safest to write the code in a very short time, where physics is clear. You don't have to worry about uh, different data types and whatnot, and everything physics is clear, and uh, you understand the concept, and then you can go on to work with the bigger codes. So that's the usual practice is followed everywhere around the world in many research groups for training PhD students or undergraduates. And that is the practice that I will also recommend. Okay, there is one question: how to get started in supernova modeling? So same. First, you do these exercises, and then you can reach supernovae. But just to bring back the fluid perspective, the same set of equations are used for modeling supernovae as well. Which are those sets of equations? These. So the same sets of equations are used to model supernovae, and depending upon which supernovae you're talking about, if you're talking about white dwarfs, then there are different equational states, which is not here. But if you're talking about, let's say, normal star, so our sun has this equational state. This is radiation, and this is normal gas. Uh, but for white dwarf supernova, you have to change this part. But these equations will remain the same. Density will become 10 to the power 7 gram or 10 to the power 6 to 7 gram per centimeter cube. Velocities will become 1,000 to 10,000 kilometer per second, and so on. So these quantities will change, the equations are same. Yeah, type 1 is supernova I'm talking about for white dwarfs. Yes. So what is remarkable or most amazing for me personally is that the same, like these innocent looking equations, which we derive or we came through intuition by looking at water or gas or air, applies to these stars, and they match with the observation very well. And that is something I think you should appreciate again and again in different contexts. Okay, so after getting practice in Python, which software we can use? So Python is not software, Python is a programming language. And to get a good grip on programming, you must do programming in a low-level language. So for Python, you do some uh, prototyping or practice to understand the physical concepts, but your production code or the code in which, even for practice, I would say you should do either C or Fortran. Fortran is becoming a bit old, but so C is now cutting edge. So C or C++ you can use. So the lower level language gives you advantage that it gets you directly to the core of computing, that how computer works, and it allows you to use computer more efficiently and also understand if you get some garbage result, then you should be able to understand that this is some numerical problem, not physical problem. So it should not happen that you run some code, you download it from internet, ran some code, and then you found some big discovery. That is, you should be careful that without understanding the code, if code gives you anything, then it should be suspicious. COMSOL, MATLAB, ANSYS, I will not say they are useful for astrophysics. First and foremost, because they are all proprietary. So you don't know what is written inside the code. You don't know how they're updating the velocity, what kind of energy source they have. So these are very like, without understanding or without open physics, you can't expect people to trust your result or whatever you find. Someone is writing Rust. Rust is very nice language, which is memory safe. So for parallelization, it is very modern. I've given some thought on this, but writing full-scale astrophysical code like Mesa with Rust requires probably tens or hundreds of students like you for 5-6 years. So if someone can do it, it will be revolutionary. Mathematica is useful for analytical computation, but it can't do large scale numerical computation of fluid simulations that we discussed today. Those are React, I don't know. React, I don't know anything about it. Okay. Which filter mostly use? I don't know. I don't do observation at all. So I have very little idea. Build a website related to astronomy, show use Python. I have no idea. Can we make multiple signs into one body problem using Poincare map? So Poincare map is not doing mapping from multiple body to effective one body or something like that. It is just allowing you to look at the data in only special sections. So you have full 3D data or n-dimensional data, but you're looking at only parts of it, which might be observationally important or allows you to understand something, relationship, so it's not mapping. It's just looking at only part of the data. That's all it's doing. Okay, so now we are actually a bit ahead of time. So if there are more questions, I can answer.
Okay. Looks like there are no more questions. And of course,
Mm.
students can ask the questions on Google Classroom if they have
Yes.
come across anything. So thank you. Thank you very much, Dr. Kashyap, for taking time out. It was really
Welcome.
wonderful two presentations, and it will definitely give a hold to students so that they can start and explore themselves further. And also, thanks to Wilson College and the
Mm.
staff there.
Yeah, thank you very much for organizing this
such a
lecture,
nice-
because this I think it goes it has much higher reach to students.
Yes.
And it connects, and this I would also love to have this Google Classroom available for quite long time, so that whenever they are progressing, going to the next stage. I'm seeing that some students are also coming from 9th class. So as they are progressing in their career, they can also maybe join some other group where they can keep asking questions and be in interaction with everyone. So
Yes,
that was
definitely.
really useful. Yeah.
This Google Classroom can become a mode of communication in future. That's right.
Yeah.
Okay. Is there any announcement you want to make, Mahesh?
No, thank you very much, sir. No
Okay.
announcement yet. We will have
Okay.
our next session at 2:30.
Okay, so I'll go now. Okay. Thank you, everyone. Bye. Take care.
Thank you. Bye.